Hi everybody, I'm the greatest living inventor, and today we are doing my invention, space escalator. So I'll write it down. Space escalator. Okay, so facilitating a space elevator for 1 kilogram weights, okay, small weights, by splitting it into many independently floating sections. Okay, this is my version for a space elevator. Okay, if you don't know what a space elevator is, my version of a space elevator. Okay, space elevator looks like this. There is the Earth. It's not what I'm suggesting, it's something else, but just that you know, space elevator, if this is the Earth, and we put something in orbit. Okay, this is orbit, like a counterweight. This is a counterweight. Orbital counterweight. So this is like when you tie a rope to a bucket of water and you rotate it, okay, or doesn't have to be bucket of water, anything, like a slingshot. You rotate something, so the Earth is holding on to the counterweight, to this something, and this something rotates. And to this something, they tie down a rope, a long rope, and on this there is some robot or something that climbs. Okay, so I don't know how to draw the robot, but it climbs on this rope. Okay, so this is not practical today. Why? Unlike my invention, which is practical today, this is not practical today. Why? Because my invention solves the main problems in space elevator, which is strength of the tether. How do you say it? Tether. Okay, this is the tether. So problems tether strength, another problem is the mass of the counterweight. I just want to point out in the tether strength that it's not just that the tether needs to carry something heavy. It's also the tether itself. The rope itself in such a length is very heavy, so it tears up itself. We don't have today materials that can hold such a weight. We can use in the future maybe carbon nanotubes, which are very strong, but we cannot make them long today. Okay, so and the third problem is getting power to the climber. Okay, so all of these are problems of space elevator. Okay, so my invention is, instead of a space elevator, to use something else. So now I will describe what is this something else. And an escalator, if you don't know, is like you have in the mall. It's like a stairway that is moving. Okay, so sorry, I'll take off my shirt. Okay, so this solves the main problems of space elevator which we've seen. If you want to see about space elevator, about what I've told you about now, there is a video. I will put it in the description of this video. Design your own space elevator by practical engineering. Okay, so now back to the space escalator, my invention. This is done by separating the long journey into many stations, stations from below to the space, into many stations, each with its own trick, according to which unique part of the Earth's atmosphere it's located in. Okay, so each layer in the atmosphere has a unique, useful characteristic. Okay, so we don't treat the whole voyage like it's the same. We realize that it's made out of different parts, and we use the advantages of each part of the surrounding. So number one is the troposphere. Troposphere this is 0 to 12 kilometers, and a hot air balloon has buoyancy. Okay, the next part 2, stratosphere. This is 12 to 50 kilometers. Can you see this marker? Yeah, you can. Layers don't mix. So we can make hydrogen, helium, methane balloons and keep them stuck in the layer we want. Keep hydrogen balloons stuck Okay, I don't have room to write everything. I'm just reading again. layers don't mix here in the stratosphere. So we can make hydrogen / helium / methane balloons and keep them stuck in the layer that we want. 3. And then they can be like a base or like something that we can hang a rope from, like we can do something with them. 3. Mesosphere. Uh, 50 to 80 kilometers. Needed to write it higher, never mind. Not enough air for balloons. Okay, we don't have enough air for balloons. But here we do something else. But this means we can pass a laser without diffraction. Okay, and I'll explain what we do with the laser later. The laser is produced in a few dedicated stations in the previous layer, the stratosphere, where I said we can stack something and make it a base. These stations have mirrors and direct the sunlight to a special station with a synthetic ruby crystal and mirrors that combine the white light beams and produce a red laser beam. Okay, so let's call it ruby with mirrors. Okay, if I'm writing small, can you see anything? Not really. Okay, sunlight. Mirrors. Plus ruby. Okay, the ruby crystal is the red crystal that we make the laser with. Okay, to produce a red laser beam. I'm referring you to Wikipedia. I will put it in the video description. Wikipedia, laser propulsion, laser pushed light cell 2. Okay, so in the article about the entry in Wikipedia about laser propulsion, you should look in the section laser pushed light sail 2. And also you can look in Wikipedia about the ruby laser. Ruby laser. Okay. So 4. Thermosphere. $80 to 700 kilometers. Different chemicals are in different layers here. So again, we use balloons filled with the lightest chemical and keep the balloon stuck like here in the layer we want. But here the balloon is filled with something else, with the chemicals that are in different layers in this thermosphere. Okay, so balloons stack according or filled with light weight chemicals. Okay. And finally, exosphere. I'll erase the title. Exosphere. This is 700 to 10,000 kilometers. Can you see what I write? Yeah. This has mainly the aurora, okay, then like the northern light or the southern light, the aurora, which means it has solar wind. Solar wind can be used to make energy to make a laser beam. Again, we are using something similar to this, and it's based on this, so it's again the same trick. So solar wind, like we wrote here, sunlight, mirrors, and ruby. Here we write solar wind, which is charged particles turned into a laser. Okay, like we had here, sunlight turned into a laser. Okay, and based on this. Here it's based on this. Sitting on this. Okay, so you can see in Britannica.com, I'll put it in the links, /technology/solar wind power satellite. Okay, solar wind power satellite. So you can make electricity power from solar wind. Okay, the laser beam here is used to push on small particles emitted by the station, which in turn pushes the station like a rocket. We don't need much thrust because we just want it to maintain altitude. Wikipedia, laser propulsion, laser energized rocket. Okay, so you can see in Wikipedia in the article about laser propulsion in the section laser energized rocket. Okay, between the stations, robotic, okay, between these stations, so in each, I'm sorry, these are the layers of the whole project, but inside, we are talking now inside one layer, okay? So, like between the layers from the beginning of the troposphere to the end of the troposphere. This is like what we are talking about now, or from the beginning of the mesosphere to the end of the mesosphere. These are the stations we talk about. Between the stations, robotic climbers pass parcels like in relay race, okay? Like you pass something in a relay race, you run, and then the other guy runs with the same package. So it's the same thing. Each robot moves up and down only on his own rope between his two home stations, okay? It's not that one robot gets to the top. Each robot, this one goes to here, this one goes to here, okay? And the next one goes like here, up and down. They don't go all the way. This has the advantage that each climber doesn't need to store energy for a long trip. This has another advantage that on the way down the robot can reproduce some of the energy like in an electric car. Okay, and in Wikipedia you can see a regenerative brake. Okay, we use braids of these cheap escalators. Okay, braids like braids of the hair, so it's like we have a few strands. We use braids of these cheap escalators for structural strength and backup. This way, if any single connection is compromised, the robots can still work around it and pass the package to the next level. This is like, and just see the time, okay, 21 minutes and a half. This is like if you are in the shopping mall and one escalator is out of order and you walk further on the floor and find another escalator that will work, that still works, sorry. So in Wikibooks, you have a link wikibooks/wiki/transportation, geography and network science, and there /resilience. Okay, resilience means if something bad happens, how do we get out of it and still work. In more advanced future designs, robots can also swing between same level stations and catch each other in the middle to reform new connections, like in that video game Cut the Rope. It's just, if you know the video game, it's like there is a creature that swings, and then if it touches another rope, it connects. It's not an important part of the invention. What if the air drag from Earth rotation pulls too much? Okay, so I'm erasing this. You've seen this. Okay, so air drag, what if the air drag, or let's write it in short, air drag from Earth's rotation. Okay, this is not unique to my invention. It also affects the elevator. It puts a tensile strength. It pulls on the string. But we are talking about my invention. My invention is very sensitive to this because it's made out of separate parts. So they really like drift. Let me show you. Like if we have the Earth. Okay, and the Earth is rotating. Let's say it's rotating clockwise. Okay, and we have this layer and that layer, and that layer, okay, of my invention. Okay, and if the Earth is rotating like this, then the air that is down where we live is going with the Earth, but so this is attracted, the air here is attracted really strongly, but the air here farther away from Earth is attracted less. Okay, so it doesn't move so fast. There is less air, but also it's not moving that fast, and it's like stays behind. So there is, in general, if this is a big arrow and a smaller arrow and a smaller arrow, it's like the air in the upside, in the upper atmospheres, it's like it's dragging behind. So it's like doing something like this, the air up. The Earth is moving like this, the air down in our level, we don't feel wind because we are moving, and the air around us in the sea level is moving like this, but the air in the very high sky might go backward. So what if this is a problem? I'm not sure it's a problem, but if it's a problem, this is not like holding your hand outside of a car window. Over short distances, the distance between our stations, the difference in airspeed from each sub-layer to the other should be gradual. But just in case, we have two options. One, not grounding the lower end, not grounding the lower end, so the whole structure is free to lean with the air drag and ease the pull tension. So if worse comes to shove, if it's the worst situation, we can let this structure move around the Earth. Okay, so the structure will look like this, but we let it go around the Earth, and we just need to track it and to know that if we need to use it now, then we are our base in the Pacific Ocean can use it, or our base in I don't know, Africa can use it. Okay, so each time it's in a different place. So this can be one solution. And two, make the whole thing in one of Earth's poles. Okay, so if we have the North Pole, let's say this is the North Pole. So here, okay, this is the pole, the North Pole or the South Pole. So here there is no, the rotation means only a twist. Okay, the rotation looks like this. It doesn't move, it just twists. It makes like a shape movement like this. So this way there is no pull, only twist. So one option is don't anchor to ground. And the second solution is build in pole like North Pole, and or let's say South Pole, because the North Pole is melting. in the South Pole there is a station of USA, so they can do it. And this way there is no pull, only twist, which can be handled with free rotating joints, where we tie the cable between each two stations. With free rotating joints. Against twist. Okay, so you understand that here it just twists. Okay. Okay, so that's it. So now I'll just describe what can we do with it. Why do we need 1 kilogram each time? It seems like we can't do anything with it. Like a spaceship is something very heavy. A person is something that, like, I don't know, like 70 kilograms. How can we, what can we do with 1 kilogram? Okay, so I'll explain. What can we do with 1 kilogram? Um, 1 kilogram each time. Okay. So I think 1 kilogram at a time. Okay, don't. Okay. Let's make it proper English. Okay. I think the coolest thing will be either, I'm sorry, I think the coolest thing will be with water, which we have plenty in the ocean. There is a book by Brian McConnell and Alexander Tolley, a design for a reusable water-based spacecraft known as the Spacecoach. Okay, so book by Brian McConnell. And Alexander Tolley. A design for a reusable water-based spacecraft known as the Spacecoach. Okay, so this is a book, a design for a reusable water-based spacecraft known as the Spacecoach by Brian McConnell and Alexander Tolley. It's by Springer. It's part of SpringerBriefs in space development. Springer. SpringerBriefs in space development. And I didn't read it yet, but it's on my to-do list. But here is a quote from this book's introduction. The basic idea behind the Spacecoach is simple. Build a spacecraft, okay, whose mass is mostly water or water-rich material at the beginning of its journey. This water is used for many purposes throughout the flight, such as radiation shielding, a heat sink, life support, and for electric propulsion. So it's like the water gives you everything, and water is exactly something that you can do 1 kilogram of, or even less at a time. Okay, so that's just one example, the best that I could find, of something that you want to do with my invention. So that's it. So I hope it was clear, and I'll see you in my next invention, and thank you very much. Goodbye.